Okay, so hello everyone. I'm glad to present you the next lecture on our school, Dr. Oleksandr Kyriienko. He's a senior lecturer at the University of Exeter, and he's leading the quantum dynamics optics and simulation group. Right now, he's going to give you a lecture on the introduction to quantum machine learning. So I'm giving you the word, Oleksandr.
Yes, thank you, Anton. Hello, everyone. So it's a pleasure to talk about quantum machine learning for this audience, and I hope you already enjoyed all the lectures throughout the week. Now we are coming pretty much to the very hot topics in quantum computing. So everything I will describe today was done within the last few years. And you should understand that unlike classical machine learning, the quantum part of machine learning is under development right now. So we have learned in these few years some techniques that work well. We have also tried many others that didn't work, and I'm pretty sure in the next few years, we will be figuring out how actually can we do quantum machine learning. So it's a very alive field. There are no textbooks, but let's try to understand some basics, build up on that, and maybe some of you will join the field and will make important contributions. Okay, so what I will do, I will be going through the slides, writing something when it's necessary. Please do ask me questions. I will open chat so that I can see what's going on. And if you have an opportunity to, let's say, unmute and ask a question, that's also fine. Okay, so let's start. Just one slide explaining where I'm coming from. And I should say that I'm actually coming from Ukraine. I moved for a PhD. It was 12 years ago, starting from semiconductor quantum optics. I have progressed then into quantum simulation, and some time ago, I have started to do quantum computing, specifically applied to near-term devices. Now I'm a senior lecturer at the University of Exeter, so it is located here, southwest of UK. And in my group, what we do is both quantum optics and quantum computing. Specifically in quantum optics, I study the regime of strong light matter coupling. So we have systems that can interact with lights, they can couple, and this is the basis of nonlinear optics. So here we have described how experimental results in 2D materials, especially in the strong light matter coupling regime, can be described by a microscopic series, and how can we enhance nonlinear interaction with in these systems. Second, I also study quantum dynamics and quantum simulation. So here, the goal is to understand how can we implement specific Hamiltonians, how can we evolve systems in time. And one example is quantum time crystals or studies of strongly correlated spin models. And finally, the topic I will be discussing today is about modern quantum computing. So the goal here is to establish the tools. How can we apply near-term quantum computers to solve the actually industrially relevant problems? And I should say we are still farther away. It's not like we can implement quantum protocols that give advantage now, but the idea is to come close to this stage within a reasonable time scale. And one specific area that I believe is extremely important is quantum machine learning. So in this lecture, what I will be discussing is quantum machine learning, learning from the perspective of motivation. So why do we want to do quantum machine learning, and in general quantum computing. So what are the recent advances that are just to move towards this direction? Second point is, how do we do quantum machine learning? Specifically, how can we construct neural networks and data embedded? So in my point of view, that is one of the most important parts of specifically quantum machine learning. And in this way, I will discuss technical details of different embeddings, show how they can be related, and apply it to, for instance, problems of regression. To have a full workflow of machine learning, we also need other tools like variational ansatz, cost operators, and I will show how can we differentiate these circuits and differentiate quantum models, which is extremely important for learning and representing certain data distributions. I will then go into quantum classification problems. And here my idea will be just to present an overview what's possible with quantum neural networks and with training. And I will concentrate my attention on possible advantages of quantum machine learning in this area. Finally, quantum SciML. I don't believe we have time today to start it, but there will be another lecture tomorrow. So if we progress to that point, I will just leave it there and continue tomorrow.
Sorry, short interruption. Your video icon, I think it's wasn't part of the content on the presentation.
Try to figure out how can I remove this video. Wait a second.
You may just put it up, like maybe in upper corner.
Ideally, I wanted to remove it completely, but maybe now I moved it completely.
Yeah, thank you.
Okay, so from this wish list, I will concentrate on the motivation, because that's the most important part to introduce quantum computing and quantum machine learning. And I'm sure you had amazing lectures already during this week explaining what is quantum computing, how we can do it, but it's never hurts to remind ourselves how is it different from classical computing. And for me, the essence of quantum computing in principle is basically in this slide, where you just take a large vector and multiply it by a large matrix. We should keep in mind that this is not a standard linear algebra. It's not something that you could take any vector, multiply by any matrix that you could construct, and that's what you have as an output. So there will be certain rules, and these rules follow the basics of quantum mechanics. Specifically, every quantum state that we start, a vector, is a vector with complex entries, but the norm of this vector will be equal to 1 because it represents a quasi-probability distribution. Second, the operators that we act with is unitary. It's called a propagator, and we know that this goes as a complex exponent with the power of minus ith, where h is a Hamiltonian of the system. So you change the Hamiltonian, you change the operator, and you could apply these operations one by one, that what we call gates, and perform quantum computing. But most importantly, we also need to read out and get an answer from our computation. And that will not be a vector, but it's actually just a list of bits that we measured, or measurement results. And we need to repeat many times the same procedure to actually get an average. So in a way, quantum computing is matrix mechanics, like Heisenberg told us, but it's a restricted and in very specific way. So here I give you my rule book when you actually try to transition from classical coding. If you don't have physics background, you are trying to transition to quantum computing, you need to understand that the rules are different. So first is unitarity of quantum mechanics. That's important. Destructive measurement process. So you measure the system, you collapse the wave function, you need to start again and collect statistics, and that operators are non-commuting because we are working with generic matrices. Also, what is very important when you build protocols, non-cloning theorem, which in a classical computing language means there is no fan out. So you cannot just take a state and then assume you have access to the same state without simulating over and over again the system. And because of non-cloning theorem, we don't violate faster than light communication. So that's good in a way, but it also restricts what we can do with quantum protocols. And I already said that we have probabilistic operation. And in this case, what you do, you have built psi wave function as a probability distribution. And when you do the measurement, you just collect one shot. So you get, let's say, magnetization of the system will be all spins up. And that's one realization with certain probability. And if you want to build a full probability distribution, you sample many times and you will get something like a normal distribution around some mean that you would like to represent. So we cannot access easily the amplitudes. For that, we would need tomography. And also, because we don't have fan out, we cannot clone this, the state. There is no simple repetition code for correcting errors. I cannot just assume that there are three exactly the same states. I measured, and if there is an error, I can just filter it out. You need to apply very specific quantum error correction techniques, and that's what very different from classical computing. Finally, if you want to build protocols, for instance, in machine learning that involve non-unitary operations, imagine that you want to invert an operator A, but that's not unitary and not Hermitian. What you need to do is extend the system size. And that's a general trick you must do if you work with something that's not a quantum in its essence. So you take an ancillary qubit, and any operator A can be embedded inside a Hermitian operator. So something that H and H dagger is equal to each other. And then every Hermitian operator you could embed in the larger unitary operator. So you add ancillary qubit, you say there will be some probability of applying H and some probability of applying H dagger, and then in total you will get a unitary operator. So if you know these rules, and if you have a background in classical development of classical protocols, I guess you could start doing steps towards quantum computing. And the motivation for quantum computing usually was the algorithmic scaling. So why do we want to make it different from, I don't know, laptops or even the high performance computers? Because even the largest conventional computer will have certain algorithmic scaling. It's based on universal operations, Boolean logic, but the number of operations that we need to apply will scale for certain problems exponentially. So I guess the most famous example will be Shor's protocol that tells us that quantum computers can solve a factoring problem in the polynomial depth in terms of number of operations, but conventional computers will have exponential scaling. However, I should also warn you that this is not a given that quantum computers can beat classical protocols. Why? Because we need to be careful with prefactors first, and we also need to be careful with absolute rates of operation. So look at this regime. You have the quantum computer that still operates slower than the classical computer. Why? Because there are prefactors that don't go asymptotically into scaling, but we need to account for those. And which means for small system sizes, most often classical solutions are better. So we actually need to work hard to find an interesting application. Second, even though there is this separation in terms of number of gates, that's very different if you actually compare runtime. Because if each operation, quantum operation, costs you much more, what you will see is that the cost will increase. And the separation shrinks between conventional and quantum computers. In the end, if you go to very large instances of problems, you still win asymptotically, but the practical advantage may be in question. So that's what you need to care when you implement near-term protocols specifically, and not just abstract mathematical, doing abstract statements about scaling. And yeah, typically the advantage in quantum computing is related to complexity classes. But as we go to quantum machine learning, especially in the near term, we need to think in terms of heuristics rather than just complexity, and see, can we outperform solutions that are available now? Another motivation that actually was my drive to join the field is the development of quantum hardware. And we get the question, at what point do curves from conventional and classical intersect? I mean, it actually becomes dependent on the instance. So we know the scaling. Let's say the scaling of quantum protocol goes as proportional to square root of n, and where n is a Hilbert space, and classical will be ON, so linearly with a Hilbert space. But that's only a statement about how it approaches n equal to infinity limit. In reality, there will be a prefactor. So you basically need to figure out, will it be 2 square root of n or 1000 times square root of n? And this constant prefactor of 1000 will actually make a difference, will shift the curve, and we need to see where does it intersect with conventional computers. Typically, doing these predictions is extremely difficult, because you can roughly estimate that if I need the depth of my circuit to scale quadratically with n, let's say n squared, and for each layer of my circuit, I would need to implement, I don't know, log n Toffolies, and then I can decompose, you will roughly get a budget. But until you implemented the protocol, until you've coded it fully, exact point where the two cross is nearly impossible to predict. And what I have seen is estimates, rough estimates, where quantum and classical protocols are competitive. So when do you have quantum computers being more efficient? But those predictions been shifted over the years. Why? Because first, you can improve classical computing protocols. You could use, let's say, use distributed memory. You could do some tricks, or even do probabilistic computing on classical computers. And this will change the scaling. But you can also improve quantum protocols. So you could reduce the constant prefactors, let's say, instead of using doubling the number of qubits as ancillas, you could use just single ancilla. And with this, you will reduce the budget by half. So then they will intersect earlier. But this is a very important question. And yes, that's why that's what you need to predict by doing simulations and roughly estimating when quantum and classical protocols intersect. In terms of hardware, we have seen amazing progress in the recent decade. So I guess officially from 2014 onward, the hardware became more and more complex to the level that I remember when starting PhD, it was we mostly were dealing with 1-2 qubits. 5 qubits for superconducting circuits was already a large-scale simulation back in 2015. But it was growing really fast, and both superconducting circuits and trapped ions now are well in the range of dozens to hundreds of qubits. We have amazing results from Rydberg atomic systems. So these are atoms that are put in the optical lattice, and they can interact strongly via dipole-dipole interaction, so repulsive or attractive. And with this strong interaction, you can make efficient 2-qubit gates. We also have seen now the huge development in photonics sector. So if you've been following companies that use linear optics plus measurement to do fault-tolerant quantum computing, or at least first steps towards fault tolerance, I believe it could be one of the contenders for the platform of fault-tolerant quantum computing. And we have seen the spin-based qubits, or molecular qubits that could be used, and many other examples. So hardware is developing, and if you are a quantum machine learning practitioner, of course, you would first start with just generic concepts. How can I code this circuit, and later it will be implemented on specific device by somebody else. But if you want to make an efficient protocol, and if you have a hardware in mind, you could actually reduce the budget by orders of magnitude. For instance, yesterday's talk by Igor Sokolov from Pascal shows that you could make a device agnostic system where your ansatz will be arbitrary, but if you tailor this ansatz to the specific system, that will make a huge difference, because you could execute it without overhead. And if you know the physics of your device, that will help a lot. Finally, from all these physical systems, we are going into full quantum computing industry. So, you know, the companies that have been investing in research and development in these areas, quantum chips are getting larger from year to year. And for instance, the slides, these slides I need to update every quarter, essentially, because IBM is coming up with a new device. So this is extremely motivating for theorists that you have devices to program. But at the same time, we need to be aware that size of the system is not everything. You have large systems, let's say with hundreds of qubits, but the operations that you can apply without noise corrupting it completely is limited. So let's say we could do it for 1,000 qubits. Recent works of this year was particularly fruitful, with works ranging up to 4,000, maybe 10,000 gates. But most algorithms that you've been learning in quantum computing which gives advantage, are in the million gates range. And we need to match this many orders of magnitude. So that's the challenge for noisy intermediate scale quantum computing. So this NISQ computing is quite restrictive because you have a system size that's big enough to make it complex, but you have noise that kills the complexity. So balancing these two, the depth of operation and the width of your quantum system, so number of qubits, becomes extremely important. But we have these devices, we can program them, test them, and that's another driver. Finally, quantum supremacy was a huge milestone achieved, which just shows, yes, we can do something on quantum computers that at certain point we could still test it with large-scale computation, but later it becomes impossible. So this task was chosen to be difficult for classical computers. Namely, you take a system and you start applying random gates. You just rotate each qubit, you apply single qubit operations, and you entangle those with specific gates, and you apply this randomized schedule until you get a state that becomes highly entangled. And getting a sample from highly entangled distributions takes exponential time on a classical computer. So I should say that the old results from Google from 2019 need to be adjusted because the predicted classical sampling nowadays, the times were shifted. So you don't actually need 10,000 years. You could probably do it in few hours. But that's the same question about the separation that we discussed. So 200 seconds versus 10,000 years and 200 seconds versus few hours. The separation certainly shrinked a lot, and simply because of better classical solutions. So they used tensor networks to do efficient tensor contraction and sampling. But if you are applying it to some financial industry, and if you need to do some sampling that is connected to trading, doing it in few hours makes a huge delay, even though algorithmically the complexity of your algorithm didn't change a lot, but the absolute time of few hours may just prohibit you to gain when you trade. And if you actually manage to do something within 200 seconds or even less, that will be much better solution. So you could justify advantage of quantum computers even without the scaling, just by absolute rates. And I should also mention that the experiments with 53 qubits since that point been improved. So both classical timelines shifted, so it became more efficient, but quantum computers became better, and the same experiments at the level of 70 qubits, you cannot beat them classically. And you could continue in principle, so there will be always a race towards the better protocols. So that was a huge motivation for everyone that you can reach a quantum advantage. You can reach quantum supremacy, but the question is, can we benefit from it? Can we reach an advantage? And that's still an open question. So whatever you will see in the press, we still need to reach to perform a large-scale quantum computing experiment that will give you actual industrial advantage. But most likely that will happen in the coming years. Okay, and one of the main motivations for me is quantum computing applications. Because if you think in terms of just like algorithmic scaling, doing something with O(n) gates instead of O(n) squared, that's mathematical statement, but what can we actually solve? And over the years, few areas were identified. So you have heard yesterday about quantum chemistry. We could also say generally it's material science, so materials, chemistry, new batteries, and high energy physics simulations. So I bunch these areas together because it's very intuitive for physicists and chemists. Why would you be interested in these problems? Because they're essentially quantum. So you have a complex quantum problem and you are trying to teach a quantum computer to represent this problem. So the idea of a simulation. And intuitively, it feels a very good fit to quantum computing. In practice, however, because you have very efficient classical solutions, like density functional theory, DFT, or molecular dynamics, you don't need to a full microscopic state of 1,000 atoms. In many cases, you actually don't need it. You would only need it for very particular problems. So if your model is trivial, like a ferromagnet, Eisen ferromagnet in 1D, then most likely you are not beating the classical solvers. But if instead you start introducing correlations, change geometry, and you start breaking symmetries, then the problem becomes difficult, and that's where quantum computers can help. But again, that's very specific to physics research. Other areas, a little bit more heuristic, that were proposed are quantum finance, but it's very difficult to understand what is actually the essence of quantum finance. So for me, it's the combination of solving optimization problems that are everywhere in finance area, quantum machine learning itself with different applications, and quantum scientific machine learning that's related to solving differential equations and specifically stochastic differential equations that you would use in finance. So all these applications are important in a different way, and we don't know yet where would advantage come from, but I can say that choosing the use case that fits all the restrictions of near-term quantum computing, that is not too sensitive to noise and doesn't have efficient classical solution, is basically the game of near-term quantum computing and ultimately machine learning. So with this, let me pause a little bit, ask if there are any questions. And what I would like everyone to do is go to chat and ask and write your opinion. What do you believe will be the most promising use case of quantum computers? So I know that the views are divided. Some believe it will be chemistry, others believe it is in generative modeling. So I'm interested in your opinion. So just write a couple of examples. What do you believe will be the future of quantum computing?
You can also maybe open the microphone.
I guess, Anton, you would need to start so that everyone follows.
Yeah, okay.
Okay, we have some options now. So quantum simulation, but let's say quantum simulation is very broad. Indeed, you can simulate nature, but would it be a battery research? Or maybe you want to simulate exotic magnetic systems. So this is a very open question. For instance, the cryptographic solution, yeah, that cryptography is a big motivation But again, would we like to break existing cryptography or come up with a new one, protected solution? So that's, the questions to answer. For instance, biotechnology for drug development. You could look at this problem from different ends. So one way is using quantum computers for optimization. So you have many drugs and then you screen, you try different combinations, and you only use quantum for optimizing on some labels. Or you actually can use it while simulating properties, but then optimize classically. Or you may do both. So there are lots of different options, and I don't believe quantum computers will be used for every part of the workflow, but just some parts that they can accelerate a lot. So molecular chemistry, it is true that classical to quantum, the hybrid approach will stay. So you cannot expect quantum computers to do the job in every aspect. And that's what I actually see in research every day, is that if you want to make something efficient, you don't try to offload it to quantum computer, but make it hybrid. Okay, stochastic processes, agree, we will discuss that. And Q gravity, I don't think it was considered well, but lattice quantum chromodynamics on quantum computers is gaining more attention. So, okay, Anton, quantum sensing, agree. So these are all very solid motivations for the field. Excellent. So let's now go into quantum machine learning basics. And I will start by recapping what you already know from classical machine learning lectures, but I will only discuss the parts that we need for convert it into quantum case. Because what I really want to take from classical machine learning is that classical neural networks of different topologies are universal function approximations. How does it work? You take an input layer. So you say there is X in, and in principle, it is a vector. You load this input into a next layer, hidden layer, by weighting it with certain functions. So you could just multiply a matrix W that accounts for connectivity. You updated the weights, and then you apply element-wise a nonlinearity function f. And the nonlinearity function can, so you weight the sum from inputs, you apply this nonlinearity, you get a new latent variable, and you will be processing layer by layer this input. In the end, what you have is the output that may have a different dimensionality. In many cases, it will. You could go from a large input like image to small output like a class of associated to this image, a label, or you could go vice versa into generative modeling where your output will be an image. But that's underneath just approximation certain functions. You have an input, you transform this input, you get an output. In many cases, at least related to supervised learning. And classical machine learning depends a lot on the tools you use. For instance, on how do you connect all the elements and weights, which nonlinearity function do you apply, and how can you train it? So there will be tools that we use in classical machine learning, and we need to understand, is there a same toolbox for quantum machine learning? So looking back in the classical methods, we have two families of algorithms. And one is related to artificial neural networks and deep neural networks. So formally something that has several hidden layers. We provide an input, we mix it up with some weights and nonlinearities, we get an output, and it's nothing more just by function of your input parameterized by the weights. We could also build quantum kernel methods, and kernel-based protocols are using the fact that the distance between points x and x prime can be measured in very different spaces. So by reproducing a high-dimensional space, for instance, by rescaling your data, you could make, let's say, you could change the problem from nonlinear classification. Why nonlinear? Because you will need to separate the boundary between the blue and red dots with a function that's nonlinear. Or you could build just a plane that separates the two if you lift it into higher dimension, in this case, 3D. So that's the idea of classical kernels. In quantum computing, in quantum machine learning, we will utilize similar principles, but we will substitute our deep neural networks by quantum neural networks or parameterized quantum circuits. This is not exactly we're not trying to mimic completely the deep neural networks, but what we are doing is developing a universal function approximation on quantum computers. So I told you before that there is a function of input parameterized by weights. Here we have a function of our input variable that's embedded in the quantum circuit. Function is an output of the measurement of quantum computer, and it will be parameterized by angles theta that define your gate operations. So the essence will be the same, universal function approximation, but the way you do it is different. It's not related to nonlinearity applied element-wise, but it's rather nonlinear operation due to parameterization of your quantum gates. And you also have quantum kernels that share similar idea that you need to measure the distance between 2 points. But unlike classical kernels, this distance comes as an distance between 2 quantum states. So if I say there is a state phi of x that is a multidimensional representation of data point x, phi of x prime, if I want to measure how far away they are, I can just compare the states. And this kernel will be measured by apply operation u for x, apply operation u dagger for x prime, and see if you return back to the same state or not. That's your similarity measure. And once we know this analogy between deep neural networks and quantum neural networks and between the kernels, we could just apply known techniques from classical machine learning by using quantum machine learning tools. Of course, the success of this problem will depend on how you build quantum model. And here I try to motivate why do you even want to use quantum machine learning. One idea is that representing data points as quantum states inherently uses the high dimensional Hilbert space. So imagine you have data. So that's your input space with data point x. For instance, it could be like a price of some item. And then depending on the price of item, you are trying to decide what should be your optimal, let's say, basket in the supermarket. So you can just take those prices and do calculation classically, Or you could load this data point into a quantum register. So you say there will be a quantum state phi of x that represents my new data point. Or you could also start with data that's quantum in principle. So for instance, you could say that this is a state that comes from quantum sensor. And in this case, you have measured something. The output of your measurement will be, for instance, a quantum state of your magnetometer, and that will be a data point that you can later process. The important message here is that what is easy to what is difficult to separate in the original data space may be separated linearly in the alleviated or feature space. So, or sometimes it's called also a latent space. So if you have data points that don't seem to you as something that you could easily distinguish, if you transform it into a new space, it's much easier to see what's going on. For instance, if I drop on you a bunch of spin configurations, spin up, down, but maybe there will be some domains and you don't know how to process that data. You will be just looking at those pictures. But if suddenly I give you the transformations that out of this image prepares you correlations from this image, so some or magnetization, which you could see as a principal component analysis, those features are much easier to analyze, because if I know that magnetization was maximal and all spins are pointing up, that's ferromagnet. If it's zero, but you see no correlations, it will be paramagnetic state. So building decision boundaries after taking data points, making them into quantum states and analyzing the properties of that quantum states could lead to very efficient separation of these data points. And one original motivation for doing quantum machine learning was expressivity of our models, because we build them in the space of exponentially many possibilities. So we have a function class that has exponentially increasing with the system size complexity. So that was believed to be one way to exploit quantum computers. But later I will show that there is much more to that. So we have these data points classically represented as quantum states. We can process those quantum states by applying unitary operations, so gates that will rotate those states. Later, we will do the measurement, and based on this measurement, we will adjust the model and say, do we satisfy the optimal loss? So did we actually solve the problem or not? So same as classical approach, but now the processing happens in the quantum space. And here is the full workflow of quantum neural networks. You take, this is assuming that you need to embed the data. So you just take a data point X, that's a value of your input variable. Could be scalar, could be a vector. Then you say, I would apply a unitary operation that depends on X and prepares a quantum state. So here is our phi of X. So we started with trivial state, we supply this X, we created phi of X, and later we would like to measure it, but in the basis we don't know yet, which is given by W ansatz with some variational parameters theta. And once we have twisted the basis, we will do the measurement of expectation values. In principle, these expectation values of operators O, measured many times, can lead to some scalar values, and the scalar values you will weight by additional W coefficients that could also be optimized, and you have your model. So your model will look like some curve or the surface, depending on what's the dimensionality, parameterized by your angles theta. And the goal is to match this function to minimize the loss that solves the problem of quantum machine learning. So I will show exactly which problems can we solve. And the essence is preparing the latent space function phi of x. This will depend on theta's parameter. It will depend on the way how you embed your variable and how you measure. So if you figure out each part of the protocol, you have built a quantum model that can represent certain process. And this model will be adjusted either variationally, or maybe if you have a good idea what is an optimal schedule, you can avoid variation whatsoever or use for some other protocols. So variational quantum algorithms for quantum machine learning in near term play an important role, but in principle, you could also get away without this variation. And yesterday in Igor's talk, you have heard about hybrid quantum classical protocols, where you just take a circuit with some parameters that you would like to tune. You measure loss function, for instance, in case of chemistry, that was energy. It could be some overlap measure or just a value of your quantum model at certain point. You take a distance between your model or quantum model and what you would like to represent, and you try to minimize this distance, so loss function. This minimization will happen either in a gradient-free or gradient-based way. So if it is gradient-based, you essentially do stochastic gradient descent on this quantum circuit, and you will be in the loop adjusting the parameters. So that's the same idea you should already know. In a way, yes, so the question is, the idea of data embedding is in calculations of the functions that will be then minimized classically. So essentially what you would like to do is take something classical, then you move it up in the sky, I don't know, some Hilbert space, where you have much more freedom. And then you will be processing operations. So you say data points are not anymore living on Earth, they were flying in the sky. You compare those data points and you project it back to Earth when you measure. So you say, I started in the initial data space. I have promoted it to a larger space, performed the comparison. I learned some correlations. I learned some properties of my data that were not visible before. And I later just concluded by doing measurements. So yes, it's building functions while using the Hilbert space. But when you have readout, it is a classical function. So it will be just, let's say, the scalar. That is true for supervised learning and specific linear regression, but maybe I would like to minimize classically the distance between the probability distributions. So in that case, your output is already a quantum state, and you don't need to measure averages. So I will explain it later in the generative quantum modeling approaches, that in that case, classical optimization will still be used, but your output is a quantum state. Okay, so we got the basics, and let me just reiterate that we have classical machine learning ingredients, which is input layer, some vector of variables x input. And what is very important that this could be discrete, this could be continuous. This could be, this could have some structure, for instance, an image. And it could also be a text. So the input layer for classical machine learning is very important. I mean, which kind of data set you use, because it defines what should be later the connectivity of the network. So image processing and processing of some discrete variables will have different optimal strategies for processing. Then you would also need to apply nonlinearity to each layer, because without that you are doing just linear transformation of your input that has limited applications. And you also need to get the output as a weighted combination of all your inputs. So in some sense, you are doing fan-in. So you start with many elements, you get one. So these are classical machine learning ingredients. What is the analog for quantum? Here, the input layer is substituted by data embedding in forms of feature map. So you either take your x and instead apply u phi of u of x, or you get immediately the quantum data. So a quantum state that is a result of measurement, but you didn't collapse it yet. Then the weights and connectivity of your deep neural networks now go into the variational ansatz. So that is unitary W of theta that rotates and searches for the best quantum state representation, in which you can either perform a measurement or compare the states. So it's either you take a cost operator and do an expectation over the state you prepared, or you would take, for instance, a kernel measurement. So between 2 points. And the kernel can go with absolute value squared, can go without. So it's any measure of distance will work. And this will be the output. Again, you will need to train your loss function. So for that, we will use circuit differentiation. And I have composed slides that detail essentially every machine learning, quantum machine learning ingredient, so we can go step by step what one can do here. Some parts like quantum feature maps are very detailed, because I believe that's what makes quantum machine learning very special. Others like variational ansatz and measurements, we could briefly discuss, but that's for you to decide, or how would you like to post-process your data. And then I should also introduce circuit differentiation. So now that we know the toolbox, let's just see where are we going to apply it. And for this, we'll need to return back to classical machine learning and see what are the tasks of machine learning. And this will be based on several types. So first one is supervised learning. You are given not just data, but you're also given the desired outputs. It could be the outputs of your function measured at different values of your variable, and the task will be regression. It could be a label associated to specific vector of x. That will be a classification, but these are all supervised methods, and that's, I guess, what you have studied before, and that's what I will be mostly discussing in these lectures. Beyond supervised learning, you also have unsupervised learning. For instance, you are given a training data, so just data points with variables x1, x2, but you don't know the labels, so you don't have desired outputs. And the goal of the program is to figure out the correlations, like inherent properties of your data set without the hypothesis what should be the answer. So that's much more complicated, and partially generative modeling is related to unsupervised learning, but we will not be going deeply in this subject, so it will be still more or less supervised case. And there is a semi-supervised learning that's somewhere in between. You try to generalize on very few desired outputs. There is also reinforcement learning that I'm not going to cover in these lectures at all. Quantum reinforcement learning is known, so it goes different ways. You can use quantum computers to optimize some action of your agent and apply it, for instance, in quantum optical experiments, but that's not. It requires a very different toolbox, so we will not be touching it in the lectures. And from this, let me concentrate on supervised learning and specifically on regression. So usually I would like to just take machine learning as a set of problems that I can solve, and depending on the problem, I will need to lay out the tools. How do I build the model? Which feature maps should I use? How do I post-process it? And because the problem itself defines the workflow, the most optimal way of solving it. And out of all problems, we will go through regression first, then there will be classification, clustering, solving scientific computing problems like differential equations, and generative modeling. And the regression is the simplest one. You are already given a set of points with labels. So x is just one-dimensional variable, y is the value of the observed instance, and what you are trying to build is a function f of x that predicts y. So which kind of problems would you like to solve? I bet many of you will be very happy to have such a secret weapon, which is build a model that can automatically predict the stock price. This highlights also the task of quantum machine learning and machine learning in general, because not only you are trying to do regression, it's not that you would like to take historical data and interpolate or like just draw some curves matching points. You also would like to generalize, because for a stock price prediction, what matters that you could look a little bit in the future. And if you have built a genuine model that can predict, at least for next few days, the stock prices, that's where you gain, but not just by fitting functions in the past that have no generalizations that cannot extrapolate to next points. So that's the goal of regression in machine learning. So we got these functions, and typically in classical machine learning, you could use some combination of functions f of x. You weight it with some parameters. You take an absolute value square distance between your function and observation. You minimize this distance, so that's called loss. That will be your answer. In quantum computing, we will do exactly the same approach. We will take an input data points xi. We will build our model. I guess here it's swapped f and y, but we could see it from the loss. that I want to compare my quantum model output and the provided label, and we could minimize the loss and learn this dependence. So if you really want to understand technical details, I would really suggest looking at this PRA paper by Kosuke Mitarai back in 2018. That was one of the first examples of quantum machine learning that was called actually quantum circuit learning. It's very much intuitive and heuristic, so there was no background as we see it now, but we could already understand some motivation, so why the processing happened in this way. Specifically, what they did is they started with some zero state, which is just 6 qubits, tensor product in the zero state. Then what you do, you apply a feature map. In this case, it's called U in to this zero state. And the feature map they apply follows this rotation, product of rotations of Ry type with arc sign of X. So what happens is I need to expand rotation around y-axis using Euler's formula. So rotation around y is just cosine of x identity on j's qubit minus I sine. But now I should mention that it was not x anymore, but arc sine of x. And here it becomes sine of arc sine. Then I repeat it on all qubits. So sine of arc sine is easy. It's just x. Then I also have minus I y Pauli operator, which I once I multiply, I will get minus 1, 1. So it's a real matrix weighted by the variable x. If I apply it to 0, it means I, for some part of the state, I will remain in 0 with, I guess it's square root of 1 minus x squared, or I will apply y. So I will flip the spin, my qubit, and get x-dependent amplitude. So I have supplied features, my states become indeed x-dependent. And then they say, oh, let's just use a variational protocol, so variational ansatz to reshuffle those elements. So no specific reason why would you take, let's say, arc cosine of x squared and RZ and not Rx, but it's just heuristics. Let's try to make something x-dependent and see how it works. And that's what they get. They actually managed to do nonlinear regressions with QNNs on different functions, and they also have seen it generalizing quite well. So you start with some initial curve, and then you supply, in this case, I believe was 50 points, and then you get your function learned. So in this case, initial heuristics work, but the understanding why, how do you embed variables, why do you build models in this way was unclear. So that's what later many researchers tried to understand, and we have some basic blocks now on in terms of embeddings and manipulating the data. And embedding goes in the way that you have your input data and you just need to represent it as a quantum state. So there are numerous ways how you can do it, and one is actually basis encoding. So imagine that you have a discrete variable x, A discrete variable can follow just 0, 0, 0, 1, 0, 0, etc. So these are bit basis states for n qubits. You have 2 to the power of n states. Each can label your data point. That's what is called an amplitude encoding, because your function of x can be just the state that represents a weighted average of each bit string with certain amplitude, complex amplitude. So that's one way of encoding data. But bit basis encoding is quite specific, because you say each point is a bit string or some specific state, but you cannot differentiate with respect to this bit string, because it's discrete. So we don't really have analytical derivatives for such a discrete encoding. And what we would like to connect later, this basis encoding, we will connect with rotation-based encoding, which is continuous. So how does this angle-based encoding work? In the same way as I have shown before. So from the quantum circuit learning, we know that if I take Ry operator as a function of x, that will be just cosine of x identity minus I sine of x, y. Here are your features. This is cosine, this is sine. And in principle, if I'm building the model, I will implement Ry operation, but also there will be Ry dagger, because I have a state psi of x, measurement operator, and another state psi of x. So the complex conjugation will give me Ry of minus x. And I will need to interfere cosines and sines. So altogether there, I am getting something like minus I to the power of x as my basis. And we will see it leads to Fourier embedding of quantum models. We can also apply scaled feature maps with an example of arcsine, but generally for any rotational gate, let's say around axis alpha, I can apply phi of x, where this is a classical scaling. And that also helps, because we sometimes we don't want to work with just Fourier basis, because we will be fitting models with Fourier polynomials. But there are many other types of bases that are beneficial. And for instance, we've been developing Chebyshev feature maps that I can show later. We have been developing the tools for finding an embedding that suits specifically the problem, and the exponentially expressing phase feature maps that I can show later are equivalent to doing basis encoding, but with continuously parameterized variables. So if I summarize the essence of feature maps, it's literally any unitary that's x-dependent can provide certain information about your data point to the quantum state. And you could apply it to zero state. You could first prepare some initial state with angles theta. So this is a variational ansatz with some theta 1, theta 2, etc. Then you apply a unitary, and you could re-upload this operation. So basically, you will be interleaving the variational ansatz with feature map, variational ansatz feature map, and that will allow to build the complex model. To understand what's going on in the system, you can consider the diagonal feature map. What does it mean? You just take a unitary s of x and you say that there is a diagonal operator that contains eigenvalues. So for instance, lambda 1, 2 to 2, lambda 2 to the power of n, and zeros everywhere else. And your basis change that leads to diagonalization can be absorbed in the W's outside. What we will see that this spectrum of my feature map essentially provides frequencies, because the exponent of minus ix and some diagonal matrix is just the bunch of exponents itself. So I'll take complex exponents that are x-dependent, interleave them with some operations that give me coefficients, and once I measured, my function will actually represent a combination of coefficients and Fourier basis. So quantum models, if they are written in this form, correspond to partial Fourier series. And there is a nice explanation by Maria Schuld and colleagues. So we could go and derive the coefficients itself, but it's not so relevant, because in reality, you never calculate those. You just apply some ansatz and see how it performs. But deep underneath, I could actually evaluate this coefficient C for every frequency if I know my ansatz, if I know my measurement, and if I contract all the indices of these operations. But what is important to note that depending on my feature map, I will supply different frequencies. So these frequencies depend on the eigenvalues of my feature map here, and specifically the difference of eigenvalues. I get exponents. I have exponents with a minus sign, and I combine them together. So some, if it's diagonal terms, will give me 0. That will contribute to a constant term. Some will be different, and I will get low frequencies, high and high frequencies. And what we care in the feature map description, how many frequencies do we have, and what is the maximal degree to which we can go. Same as in Fourier series. You have your partial Fourier series. You don't go into infinity. You have discrete frequencies. Then your capacity of representing something depends on how many frequencies you have, what is the degeneracy, and how far you could go in terms of maybe high frequency response. If you have a signal that oscillates a lot and your model is poor, it only gets slow oscillations, you will never be able to represent it. Vice versa, if your data has some smooth, slowly changing dependence, and your model contains mostly high frequencies, you will be getting the results that are too oscillatoric. So that's what you need to pay attention when you solve quantum machine learning problems. And with this size and degree of the spectrum, we come to the key properties of quantum models as we build them. So we design feature maps based on different number of reuploadings, applying operations in parallel, so on each individual qubit or in series, or maybe we can interleave both, and it's basically up to your imagination. How can you build this model? But when you build it, you need to understand what will be the capacity. So how many frequencies do you actually encode? The general rule is that the more times you apply the feature map, either in series or in parallel, the higher will be capacity of the model. So the larger number of frequencies you would have. And capacity is good if you know my data is very complex and it follows, it can be represented in certain space of functions, say, fine, that's what I need to do, just build a very powerful feature map. But there is also a point of expressivity, because applying feature maps by itself will generate frequencies. But if you cannot access each frequency individually, each term in your expansion, and if you have coefficients, even if they are non-zero, they are constant, you will have a limited ability to fit this model to specific data. So one example comes from just take your variational ansatz with some random theta's and see what are the coefficients in front of each frequency, starting from zero frequency, going to higher frequencies. And you could see that the coefficients that you generate for, let's say, lowest component, C1, can still have some sufficient spread. But as you go to higher and higher frequencies, the redundancy disappears, so you will have smaller and smaller opportunities for fitting it, which naturally provides regularization. But if your task is requiring your high frequency tuning, this model will just not work. So you will need to change the circuit sequence. And once you have built a model, you also meet the problem of trainability, because it's actually quite difficult to search for optimal parameters of the non-convex optimization problems if you have many parameters. So formally, it's defined as that the variance of the gradients of your variational angles will decrease with system size, because if you have many options to search, naturally you would expect it becomes difficult to come to an optimum. And since it's non-convex optimization problem, you don't have a proven convergence to the global optimum. You can be trapped in the local minima, and that's actually what happens. You either trapped in you either go very slowly, converge slowly, or trapped if your ansatz is not suitable. So that's another point you need to be careful with. And if you did everything right, so we have high capacity, expressivity exactly matching what you need, and it's also trainable, that's amazing results. So you could do a lot, but it's a very non-trivial task, and it's a challenge of current quantum machine learning. How do you make sure that these elements that compete with each other, so high expressivity makes poor trainability and vice versa, how do you optimize those and build a perfect model? And at this point, I will just stop to take a few questions. And wait a second. Anton, do I understand correctly that we are finishing?
Yes. We finish at 12, or at 12, like our time.
Let's
in 7 minutes. In 7 minutes, like our lecture officially finished.
Okay, so let me just do the following. I will quickly go through the advanced part of quantum feature map building, because I do realize it may be too technical, but if somebody can get at least a part of information out, that's fine. So and
we can use like 10 minutes from the break also if it's important. It's fine.
No worries. So I will prepare as a stage for tomorrow, and then so the feature maps that I have described before were using the Fourier components, but what we were doing in my group is the feature maps that first have increasing capacity and feature maps that use different basis sets. For instance, what is known as a Chebyshev polynomial basis set. So Chebyshev polynomials are the functions of x that look like t of 0 of x is just constant, it's 1. T1 of x is linear. T2 of x, if I remember correctly, is something like 2x minus x squared. So you get the polynomials that with increasing degree n add you components with linear, square, cubic, but they also have this mixed terms such that you could make them orthogonal at a certain point. And if you bunch rotations with weighted arccosine operations, what you will see is that you actually generate the Chebyshev states. And these Chebyshev states can have the model with increasing degree, with maximal degree dependent on how many times you applied your rotations and what was the prefactor. And in this, what we call the Chebyshev tower case, you will have a highly expressive model. The second example that I want to highlight is a phase feature map. The phase feature map is utilizing the properties of a quantum Fourier transform. So you say that if I take a state 0 and I apply a Hadamard operation to this state, I prepare superposition of 0 plus 1 over square root of 2. If I additionally apply a phase rotation, which depends on x, but also has this very peculiar prefactor, 2 to the power of j. What you will be building is fractions of your 2 pi that decrease exponentially. But if you interfere them together, so you have individually all rotations and combine them together, your state now will include all possible combinations of x. And you will have each frequency from 0 frequency to 2 to the power of n minus 1, which is an exponential capacity, and individual state x tilde will be based as on a Fourier representation of your quantum state. So in the end, you have a model that looks like this. You have exponentially many frequencies and some coefficients c that are based on your variational ansatz or generally quantum circuit. Now, what I want to do is take those states labeled by frequencies and go into the computational basis state. And we know that there is a quantum Fourier transform that can map basis states to frequency states. And I just want to go the other way around. So this mapping is performed by the discrete Fourier transform matrix or quantum Fourier transform circuit. So I just take a bit basis state, go to Fourier representation. I can go the other way around. And my goal will be to develop the quantum circuits that simultaneously can load data in the exponential space and can map them into computational basis space. So we know that quantum Fourier transform circuit explicitly can be built as some Hadamards and controlled rotations. So this is independent of x. But if I go the other way around, I can start with a state that has some x information, and I can prepare the x as a bit basis. So mapping between two different bases becomes important when we actually do solve problems in generative modeling. Why? Because what I want to do is differentiate the model first with respect to my variable x, and second, I want to be able to build it with a fixed number of frequencies as compared to basis states. So here's an example. I just take a 0 state, apply Hadamards, do rotations, and at this point, what I have is a Fourier model. if I apply the inverse quantum Fourier transform, I will get the basis embedding circuit. But I could also just remove it. And if I don't have the Fourier transform circuit, I'm building my model in the Fourier space. And this Fourier space may have a reduced number of frequencies. So I have tuned my model with some Fourier components. And after I learn this model, I can map it to the bit basis by just reverting the quantum Fourier transform. So this is a specific technique we've been developing, and so in this preprint, and we also been using it now for various generative modeling tasks. So that's one more addition of what can you do with quantum feature maps, just to show that yes, it's an ongoing research. How can you build high-performing models? How which polynomials do you use for these mappings, and how can you efficiently apply it later to solving problems? And I should stop here, and next time we'll just consider the different types of quantum ansatz. So, for instance, that you could take a hardware efficient ansatz to manipulate your data, that you could choose your gate parameters to lead to real only amplitudes that will help for certain problems where you would like to represent only symmetric and real states, or you could have QA ansatz. And in general, sky is the limit. You could come up with your own circuit and see how it works. You could also do different measurements. So you choose a set of operators that you would like to measure. Typically, we will take, let's say, expectation value of the operator on certain qubit, or we could also sum them up together for all qubits in the chain. Or we could also include, let's say, pairwise correlations. We could multiply them by any weight functions that we want. So again, the measurement part is up to you. Maybe you would like to do it in the X basis instead. It really depends on your feature map and the variational approach that you apply. And finally, I will stop here saying that once you have formed models, you need to train them. So next, we will go into quantum circuit differentiation techniques. So I'll thank you for attention, and I will take the remaining questions. Yeah, so the question is about non-convexity of these protocols. Why is it non-convex? Because unlike problems where you have some fitting function multiplied by the weight, so non-convexity means if I differentiate twice with respect to the parameter I would like to optimize, my second order derivative should be positive if I have the convex problem. So that's basically just saying that if my problem is like this, I can always go down in the landscape. So this is parameter t that I would like to tune. If I know that my landscape is always pointing up and there is a unique global optimal for the problem, it's a convex optimization problem. Non-convex, it's because we have f of x as a function of theta, where thetas enter in a very specific way. Because if I applied some feature map, later I will be applying the parameterized circuit, so doing some measurement and then u phi of x. This is based on some Pauli operators, p and theta. But it leads to cosine of theta 1 minus I sine of theta Pauli. And because you don't have a linear function of theta, but you have sines and cosines, you will quickly see that, there is no way you could have only positive second order derivative for your loss function. So in general, if you want to make quantum problems convex, you need to rewrite the way how tuning parameters enter. One way is using kernel methods. These are convex, but there are some drawbacks to that in principle, like it requires a bit longer discussion. Okay, so let's see. Increase in number of qubits, decrease in number of gates. It depends. So it is true that if you increase it in width instead of the depth, you actually can win. That is true. For instance, it doesn't matter if you want to make feature map expressive. You could just take more qubits instead of larger depths. That would help. But now you enter this different problem. If you increase it in width but don't have any depths, you do not correlate the qubits. So let's say qubit 1 and qubit 100, if they are not connected, can be treated separately. So if you don't have sufficient depths, you will never make qubits interact with each other. And that means that you can have classical models that performs as well. So you need to simultaneously increase the width and increase the depth just to the point that you could optimize it. If you take 2 qubits and have a depth of 1000, probably that was not the great protocol. If you take 1000 qubits and have a depth of 2, you could also simulate it independently for taking just a bunch of pairs. But if you have let's say 10 qubits with a depth of 10, that most likely will be the complex model. Current implementations of quantum machine learning on quantum computer, is it possible by designing quantum computer with specific gates? Yes and no. So if you want to just implement any quantum machine learning, you don't need protocol. You don't need to make it specific. Arbitrary rotations in front, arbitrary operation like C0 followed by other rotations will do the job. The problem is that if you want to make it efficient, so if you don't want to search in the entire space, but make it the most compact representation of the model for that device, then yes, then you will need to think about specific gate sets. So if I don't have C0s for Rydberg atoms because they operate in terms of ZZ coupling, why do I need this Hadamard to convert C0 into CZ? I don't. In principle, I can just live with native couplings and optimize it. So to make efficient, yes, but if you just want to show that it works, you don't need to care about specificities of hardware. How did you validate the QML model compared to classical ML procedure? I mean, how do you validate in general QML models? Because it's a non-convex optimization problem, you basically need to run for different benchmarks models, separate circuit structure. and see how the average loss performs. If it's classification, you will run the F1 score, or if you will run some accuracy tests. So it is a difficult problem, because if you know that there is some optimal model and it's convex optimization problem, you will just compare the performance of your classical and quantum model, and you declare, yes, we've reached the global optimal and it's better for quantum. But because of non-convex optimization nature for these QNN-based techniques, you are in the heuristic regime. It either works perfectly, and then you could analyze, why does it work? Why do you choose specific measurement in terms of Z operators and not X? But it is still heuristic. The actual training, the experimental implementations. Yes, so there are experimental implementations, and I will actually discuss them in the future. So, so in the next lecture, it is possible to perform, let's say, classification on a quantum computer. What you do is you take a data set, and then you need to convert this data set into features that can be loaded into a quantum computer. So your feature X should be continuous and should go between 0 and 1. So it is normalized. Why? Because if you don't normalize your features, your variable X, you will be rotating through the 2 pi over and over again, and some points will become the same in the quantum space, even though they are not in the original data set. So that's first what you do with your data set. Then you cannot load 1 million features, because it will at least require 1 million rotations, and then to make it high performance, you would actually need to re-upload it. So realistically, you talk about data sets that are small, but each feature is, let's say, complex. So maybe you perform some dimensionality reduction, like principal component analysis, and you load principal components, or some other techniques. And the implementation so far on Rydberg atoms, it was graph machine learning. So studying properties of graphs. IBM did classification in 1D and 2D with kernel methods. Google shows the examples from classifying quantum states and phases of matter. IonQ, if I remember correctly, did generative modeling. So there are a bunch of implementations at smaller scale, but yeah, we are yet to find large-scale quantum machine learning applications. Okay, good. I guess we are fine for now. So thank you very much for attention. And Anton, you as a chair.
Yes. Thank you for the great lecture. It was indeed, it's super cool. So see you then tomorrow with the continuation on scientific quantum machine learning.
Yes, I would probably still talk about classification in the beginning, because it was a little bit slow, but I'm sorry if I took more time. I just better to spend more time now rather than rush and have your attention essentially scattered. Good. See you, everyone. Enjoy.
Yes, see you. Have a great day.
Bye-bye.
Bye-bye. So our next lecture starts in 15 minutes. And it will be a workshop on quantum neural networks. So yeah, and right now we're having a break.